Okay, welcome everyone to this Schemy summary in algebraic geometry. So essentially we're done with schemes. Essentially we're ready to go to sheaves, sheafification, the sheaf of modules, and kind of the last topic I really would like to address in, modern algebraic geometry. And then we are going to really modern algebraic geometry, maybe taking a few detours along the way. And really modern algebraic geometry for me means computational algebraic geometry, because all we have seen is actually computable. That's a bit surprising, but it's actually really computable. Or like the linear one, the whatever, tropical algebraic geometry. Both of them are a lot of fun. And yeah, we'll see. But first, let's just finish and wrap up the story, which people usually call modern, as I said. And I'm essentially just going to recall what a scheme is, because that's the object of study in algebraic geometry. Yeah, so let's have a look. The one definition is missing. I showed you essentially everything, but everything. So if you just rewatch my previous videos, you will learn everything about the universe, obviously. So what I mean is everything I wanted to say about schemes, except one thing. And this is, we also have seen it. So again, doing schemes is a bit somehow boring because it just repeats what we have seen for algebraic varieties. But we just need to do it anyway. So let's just recall. Recall is always good. Summarizing and recalling is not so bad. So kind of one of the key definitions that you will at one point see in your mathematical life, maybe even in your life in physics. I don't think I have seen manifolds anywhere outside of physics or mathematics. I might be wrong. Correct me if you've seen them somewhere else. But anyway, so manifold is essentially something that is patched together from patches. Like the manifold would be a pair of pens, and the patches are the patches on the pair of pens. So something that is patched together from disks. Maybe this is a more standard picture. A circle is a manifold, and it's patched together from one-dimensional disks, which are really just intervals, right? And some nice overlapping way, right? Each little patch is a very simple object, an interval or a disk, and they're overlapping, and the overlapping makes it, and overlapping in this global picture of patching makes it very interesting. And kind of we have seen that the general notion of a variety is something that is patched together from affine varieties, up to a Hausdorff condition that you need to add to make it kind of reasonably nice. And a scheme, a general scheme, is essentially the same. It's something that is patched together from affine schemes. So affine schemes is this idea of just having a spec of something. We'll come back to that later. But essentially, the story goes through. So a scheme should correspond to a manifold. Yeah, so something that's patched together in a certain way from affine schemes. And if you just repeat the definition for affine varieties, you immediately end with what people call a scheme, up to the technical conditions. Because actually, what people call a scheme is a little bit like what people call a manifold. So it depends what people call a manifold. So sometimes manifold has this condition added, sometimes it doesn't have this condition added, where this condition is just X. And for schemes, it's kind of the same. So some people throw words at schemes, some people don't throw words at schemes. But anyway, the words you usually read is reduced, finite type, and separated. Whatever those are. I'm going to briefly explain what those are. But in case you hit them somewhere, it's related to this idea that maybe the general definition of a manifold also has too many kind of strange examples included, and you don't want them. So you add a few natural conditions to get rid of the funny examples. And you essentially do the same here. And the natural conditions are the following. So finite type is essentially a finiteness condition on the cover. So maybe you want to be coverable by finitely many pieces, something like that. Separated is a Hausdorff type condition. Yeah, you can separate points in a certain sense. And reduced is maybe the most important one. It really says you have no nilpotent elements in the rings of regular functions in those guys here. Nilpotent is really the matrices that are upper triangular with zeros on the diagonal. Nilpotent matrices. So somehow you kind of kick them out. It's kind of reduced means no nilpotent. Finite type, some finiteness condition. and separated a Hausdorff condition. And that's what you usually read, and I warn you again, depending on what your reference is or who you are, if you're defining this yourself, you might add this to the definition of a scheme or not. In either way, in either order, whatever. Sometimes some of them are added, sometimes none of them are added, sometimes one of them is added. You get it, it's a mess. Yeah, in mathematics, anyway, not just mathematics. Put two people in a room, they will not come up with a general strategy how to leave the room. There's no way that this happens. And now put a few mathematicians, and they will not together, and they will not come to one conclusion what the correct definition of object X should be. Just impossible. Anyway, so I will tell you in a second where those conditions really come from, and then you want to relax them maybe or maybe not, depending on who you are, as I said. And the whole point is that varieties are schemes, and we always have seen those type of isomorphisms and whatever, affine varieties here and some ring condition on the other side. And yeah, so affine varieties are affine schemes, a certain type of affine schemes. Exactly the same goes through in this general scheme theoretical setup. So varieties correspond to this perfectly the separated reduced schemes of finite time. So three little words that we just learned: separated, reduced, or finite time. And then you kind of want to take one of them out or not, depends what you would like to do. But in the scheme world, it's kind of the point. You have some more flexibility. So you have some richer structure. So whether you have x squared equals 0, whether you have x equals 0, you somehow can't see this in the variety world, but you can see that in the scheme world. It's a little bit more of a generalization. So that's why we did schemes. Essentially everything goes through for schemes, S go through for varieties, but schemes are a bit more general. They kind of fit in this pretty nice framework of just algebraic geometry. Say it again, it's the idea of putting geometry into algebra, and schemes just pushes that to its uppermost limit, because you essentially forget about geometry altogether and just study algebra. Fine. And you still may want to make sure that geometry is included in what you do. And yeah, varieties are schemes. So summary essentially is the spec, the affine schemes are the prime ideals. Yeah. So kind of you get rid of all geometry together. You're just studying ideals in a ring. And kind of funnily, that corresponds perfectly, not perfectly, it's a generalization of the varieties. It's kind of nice. And you always have the Zariski topology. I'm going to liberally to ignore them. But anyway, you had the affine ones, which were spec of a ring, spectrum of a ring. We had the projective ones, where a proj of a ring, exactly the same, but there's some grading, and you take the homogeneous ones. The general scheme is kind of the patchwork idea, and this is kind of the scheme world. And for affine varieties, there were affine varieties, polynomial solutions, there were projective varieties, solutions to homogeneous equations, and there were the general varieties, which is a patchwork. So it's exactly the same story. And up to some slight technicalities or kind of brilliant ideas that you need to make regular functions work, which I discussed in the previous video, all the rest just go through as you would expect it. Kind of very, very nice. It's really just a generalization. You get rid of all geometry, you can focus on pure algebra, and that's actually not bad, right? So first of all, algebra should be easier than geometry. So the whole point, somewhat where computational algebraic geometry can kick in and is so powerful, is that algebraic geometry is mostly algebra in the end, right? In algebra, you can run algorithms in algebra. So algebra is good. And kind of the point, so we beefed up here really means that, okay, schemes correspond to general rings, while varieties just correspond to certain types of rings, if you want. And in scheme world, kind of the whole point, in scheme world, we can distinguish fat points, multiple points, where in the algebraic variety world, we simply can't. Yeah? Just what it is. And this is like somewhat worth the effort if you want. So both of them taken together is somewhat worth the effort, or three things taken together is somewhat worth the effort. So the green one, the blue one, and the one that I just said in words, algebra is amenable to algorithms, while geometry is not necessary. It's more difficult to put geometry into algorithms. And all of them together kind of justify, for me at least, the study of schemes, although it is pretty abstract, right? So you're studying ideals in a ring. That's not nothing I can really imagine, if you want, right? So it's kind of a little bit difficult. But just keep in mind, I said it again, kind of the whole point is that we can now distinguish multiple points. And classically, there's nothing like that. But it actually gets pretty interesting if you go to higher and higher order points. They're usually called fat points. The double points are really just the x squared ones. But for triple points, these are kind of three-dimensional algebras, if you want. Then you will see kind of the obvious generalization of this one and a non-obvious version of it, which is like this cross type thing. Let's try to explain that, why you would call that a triple point. So and intuitively, x squared equals 0 is like the red line here, yeah. But you kind of run it twice, okay? Right, x squared, y squared equals 0 is a blue line, yeah. But you again someone run it twice because it's y squared. And xy is a cross itself, but you run it once, right? Because it's just xy, yeah? So you run it once. So now take everything together, you have 2 plus 1 at every coordinate axis, so you kind of have a triple point. Calling it a point is a bit of a stretch here, but that's somehow how we can somewhat measure multiplicities in a space. You know, it's kind of a nice geometric picture. And on a scheme level, you easily see that, because this thing and this algebra, they're just not the same, and the one where you completely forget the multiplicities would just be k, and they're all not the same, so all of these are different as schemes. Anyway, I hope you enjoyed this video, and I also hope to see you next time.